Today we're going to be discussing atomic theory, basically how we thought the atom was throughout the ages. The first notable person that we are going to be discussing is Democritus. Democritus was a philosopher in the 5th century BCE. And basically what Democritus thought was that matter could not be divided into smaller and smaller pieces forever. He thought that eventually you would reach a piece that could no longer be subdivided, and he decided to call that piece atomos. A meaning not, and tomos meaning to be cut. So basically he decided to name atoms cannot be cut. His model of what an atom was, he basically thought that different atoms had different shapes. Some were pointy, some were smooth, and so I've drawn some examples here. These were in 3 dimensions. He thought that they were kind of spherical, but we have a little smooth atom and we have a little pointy atom. There was a long time between Democritus and our next notable figure. Our next notable figure came along in 1803. His name was Dalton. Dalton put forth some postulates. Postulates are basically just theories or ideas of how atoms worked. And so Dalton had 4 postulates, the first of which being that all matter was made of atoms. The second being that compounds were made by joining elements together. The third being that chemical reactions are combinations or separations of atoms. And fourth, that atoms were indivisible. So those were Dalton's postulates. He basically just took Democritus's atom model. He agreed with that for the most part. He thought that they were spherical and they were round. Spherical and hard, I should say. But he also thought about what chemical reactions actually were and how compounds worked and how we could have a more complex world than what was originally presented by Democritus, who thought that basically everything was just one type or its own type of atom instead of compounds and more complex structures. So that was Dalton. After Dalton, in 1898 came J.J. Thompson. J.J. Thompson actually performed an experiment to back up his theories. Thompson ran the cathode ray tube experiment. Basically what he did was he passed electricity through a vacuum tube. When he did that, he found some things out. Some of the things that he found out that the cathode ray had to be made up of something that was negatively charged. And he also figured out that the cathode ray was actually made up of particles, and that those particles were very, very small. He thought that atoms had a bunch of tiny negatively charged particles inside of them. We would call those electrons. But overall, that atoms were neutral. Thompson was the first person to really postulate or think that we had positive and negative charges inside of atoms, I should say. And his model is known as the plum pudding model. We don't really eat plum pudding anymore, so kind of think about this more as like a blueberry muffin. He thought that the batter or the cake mix for a blueberry muffin was overall positive, but that we would have solid negative spheres basically throughout our atom. So we had our solid electrons surrounded by a positive fluid, liquid, is what J.J. Thompson thought. After J.J. Thompson, in 1909, we had Rutherford. Rutherford performed another experiment. His experiment is known as the gold foil experiment. What he did was he shot positive alpha particles at gold foil to see just what would happen. When he did that, he saw that the majority of those alpha particles were able to pass through the gold foil without a problem. But some of them were deflected. They didn't go straight through, they kind of took an off course. So what he discovered from that was that atoms were actually mostly empty space, which is why those alpha particles were able to go through pretty easily. But that there was a positive, hard center in the middle that would repel some particles sometimes. His model is called the nuclear atom. We have a hard, dense nucleus in the center where we have all of the positive particles in the middle, and then the electrons are just kind of free floating around. After Rutherford, we had Bohr. You have most likely seen a Bohr model of an atom. This is probably the thing that you are still seeing represented whenever you look up atoms. Bohr's model in 1913 took what Rutherford said and just added a little bit more. So he agreed that atoms had a positive center and that the negative electrons were surrounding it, but he didn't agree that the electrons were just kind of willy-nilly floating around. Instead, he postulated that the electrons were in orbitals and set energy ranges. And his model is known as the planetary model. You'll also hear it referred to as a Bohr model. After Bohr, we had Schrodinger. You may have heard of Schrodinger from Schrodinger's cat. Maybe, maybe not. But Schrodinger won the Nobel Prize for Physics and is considered the father of modern quantum physics. Schrodinger had a thought experiment, and basically what that thought experiment was that you would have a cat inside of a box, and inside of that box was a radioactive element that was able to decay. If the element decided to decay, it would kill the cat. This is only a thought experiment. No cats were harmed in the making of this thought experiment. It would kill the cat. But you would not know if the cat was alive or dead until you opened the box. This thought experiment helped Schrodinger to explain what he thought that the electrons were doing. Basically, what he thought was that you could not know both the location and the speed at which electrons were moving at the same time. The cat is both alive and dead until you open the box. The electron is both here and not here until you look. You can't know both the speed and the exact location of an electron. That was Schrodinger's idea. And then we had Chadwick. Chadwick added just a little bit more to our atom. He confirmed the existence of a neutral particle inside of the nucleus. That neutral particle is known as a neutron. Neutron. Yeah. Okay. And that the neutron has approximately the same mass as a proton. Both Schrodinger and Chadwick have very similar models of the atom, both of which are still accepted today. These are our modern atom representations, our modern atom structures that we believe to be true. First, we have the wave model. The wave model comes right along with Schrodinger, where we have no certain electron position. We just have kind of an area of probability, a vague, shadowy area of probability of where the electrons may or may not be. but we can't know exactly where they are. We also have what is known as the quantum model. I know this picture is very lovely, extraordinarily difficult to draw the quantum model on paper. Just know that with the quantum model, my electron clouds are in 3 dimensions. And instead of just all electrons have an equal probability of being vaguely in a certain area, the quantum model says that each electron energy level will have a certain bubble of probability. So these are actually the p suborbital, and we get kind of these weird dumbbell shapes. So we are like 98% sure that electrons that belong to this p sublevel are going to be inside of this little barbell. That's basically what the quantum model is. Both the wave and the quantum model rely on probability instead of set orbits, and both are accepted models of what the electron what the electron's behavior is inside of the atom. The wave model is what you would more see if you were to look at an atom, just kind of vaguely electron cloud around that nucleus. And the quantum model is more detail on the wave model, where we're saying that specific electrons probably exist in this specific area of the electron cloud, maybe. Okay, there's a lot of probablys, maybes, most likelies going on with this because we are dealing with quantum physics at that point.